Okay. So welcome back to VMCAI'. I'm Vincenzo Arcieri, and I will chair the next section about privacy and security. We have two technical talks, 25 minutes each, both from remote. So the first talk is given by Depeng Liu. So if you want to share, hi.
Okay. Hi, hello.
Want to share your screen, and we talk about verifying pufferfish privacy in hidden Markov chains, Markov models. Sorry. So, okay, perfect. The floor is yours.
Okay. Thanks for the introduction. Hi, everyone. I'm Depeng Liu from Institute of Software, Chinese Academy of Sciences. This is a joint work with Bow-Yaw Wang from Academia Sinica and Lijun Zhang from ISCAS. Nowadays, privacy has been a hotly debated issue. So let's consider here D is a database containing private individual information. And there's a data analyst who wants to ask the database query queue to gather useful information. However, we want the individual privacy in this D to be maintained, and it proves to be hard to do so. So Dinner and Nissim have already proved that the entire information of the database can be reviewed by publishing the results of a small number of queries. So how do we deal with that? Differential privacy is a technique which has been applied in many famous applications in the databases. Instead of responding QD to query Q, it adds random noise to QD and reveals the noisy value, MQD, to the analyst. So it's a technique that is actually treats accuracy for privacy. And the mechanism here of adding noise is called a differential privacy mechanism. This DP mechanism is usually parameterized by a privacy budget epsilon. And here is the definition of differential privacy. Let epsilon be a non-negative number. A mechanism M is said to be epsilon dp if for every pair of adjacent databases D1 and D2. Here, adjacency means that D1 and D2 differ in at most one record. And for every subset E of the range of the output M, we have that the probabilities of getting the output in E on two databases, D1 and D2, after the noises are added, are mathematically close. That is bounded by this factor E to the epsilon. And here, usually smaller epsilon indicates stronger privacy. However, differential privacy has its own limits. It makes no assumptions on how the database is formed. When correlation between individuals exists in the database, privacy may still leak. So take an example here. Suppose X is a highly contracted disease, such as COVID-19. An entire family would have been infected with this X, or none would have been infected. And we consider the database composed of Bob and his 9 immediate family members. At this time, a query is asked, how many in Bob's family have this disease? The true answer can either be 10 or 0. And in order to protect privacy, epsilon dp is applied to the query, and a Laplace noise is added to the true answer. So here I show the PDF of the Laplacian distribution. And the answer 12, after adding this noise, is E to the 10 times epsilon times more likely when the true answer is 10 than when the true answer is 0. So Bob's information is easily inferred by the answer 12 in this situation. then the privacy is leaked. So Kiefer et al. Produces Pufferfish Privacy in order to cope with this problem. Pufferfish Privacy is a new Bayesian privacy framework which allows assumptions on the database. So here's the definition of Pufferfish Privacy. Let S be a set of secrets, such as Bob has the disease or Bob doesn't have the disease. And S pairs is a set of discriminative secret pairs, such as the pairs I just introduced. And D is a set of dataset distributions scenarios. A possible scenario here is that Bob and his 9 family members, and we have an epsilon, which is also a non-negative number. We see that a mechanism M is epsilon pufferfish private if for all the outputs are in the range of M, for all the secret pairs Si and Sj, and all the distributions scenarios theta. We have the following equation holds, which means that the probability of getting R on the secret Si and the assumption theta is no more than e to the epsilon times the probability of getting R under the secret Sj and the assumption theta. So here's the definition which perfectly describes the scenario here. The Bob and his 9 family members is the assumption theta here. And whether Bob has the disease or not are the secrets here. So whether he has the disease or not, it won't lead to much probability difference when the same answer is revealed. That's the meaning of this definition. And it's proved that differential privacy is subsumed by Pufferfish privacy on the independence assumptions on the database. Next, I will introduce the main contributions of my work. We propose the first verification framework for epsilon pufferfish privacy by specifying privacy mechanisms as hidden Markov models and analyzing privacy requirements encoded in the SMT queries. We studied the pufferfish privacy verification problems on HMMs and proves the NP hardness of the problem. We then designed an automated verification algorithm and implemented into a tool which could catch privacy breaches of the specialized mechanisms. So even for differential privacy, our tool has advantageous performances compared with the state-of-the-art tools on finding the privacy budgets epsilon. Take the truncated geometric mechanism as a running example. Here, let X denotes the set of data entries. So a data set of size n is an element in X to the power of n. And we consider a counting query F here, which will gives an output from integer from 0 to n. And we let alpha be a number in the interval 0 to 1. The truncated alpha geometric mechanism will output fx plus z with range in 0 to n, where z is a random variable with the following distribution. Here, this distribution is just like the geometric distribution, but the difference is that the infinite sequence of integers probabilities are accumulated and further assigned to the boundary values. And it's easily to prove that the mechanism is minus log alpha differentially private for any counting query F. So next is to model the truncated geometric mechanism. The log2 DP mechanism with range in 0, 1, 2 is as follows. Here, these columns stands for inputs, and the row stands for outputs. The entry stands for the probability of the corresponding output. And then we can turn the inputs and outputs into states here. We have 6 states. And we can encode the probabilities into transitions from states to other states. This is actually a Markov chain model. And furthermore, we can even use observations on the states to reduce the state space. That is, in the state 0, we have the probability 2/3 observing 0 and 1/6 observing 1, and also 1/6 observing 2. Here's actually a hidden Markov model. So the key idea to model the mechanism is to formalize the inputs and outputs as states, and we encode probabilities into transitions or into observations. Next, I will introduce the hidden Markov models. Here's the formal definition of an HMM-H. It's a triple K omega O, where K is a Markov chain, where S is a set of states, and P is a transition distribution. And it also has a finite set omega of observations and an observation distributions O, such that the sum starting from the same state of observing all the observations are equal to 0, or is equal to 1 for every state S. And here is an easy example showing an HMM. Here we have 3 states, H, L, and N. In the state H and L, we have observations of C song or C rings. So run follows a sequence of states would be H, L, H, H, L, L, H, which at the same time emits a sequence of symbols such as song, song, rings, song, song. And this explains the feature of the HMM, which is partial observability. So states cannot be observed, but only outputs of the mechanisms can be observed, which caters to the process of producing outputs with different probabilities in Pufferfish privacy. I will simply analyze Pufferfish privacy in the HMM model. The privacy assumptions and the secrets are usually formalized into the state distributions of HMM. For example, consider a dataset of a highly contagious disease about Bob and his family member. This is an assumption. A query is asked, how many in Bob's family have this disease? And in order to protect privacy, the truncated 1/2 geometric mechanism is applied to F. Here, we can know that the true answer can only be 0 or 2, since the disease is highly contagious. So the prior distribution of the true answer would be pi equals to pi to p, 0, 1 minus p, with p an integer in the interval 0 to 1. And the discriminative secret pair here is that Bob has the disease and Bob does not have the disease. With the prior knowledge and the secret, the new initial distributions are pi1 equals to 001, which corresponds to its answers with answer 2, and the pi2 with equals to 100, which corresponds to the answer of 0. Next step is to compute all the observations probabilities under the 2 initial distributions. For instance, we compute the probability of observing 0. That is pi1 times this vector, which stands for getting the corresponding observation 0 in each state. It equals to 1/6 and the pi2 times this vector equals to 2/3. The ratio of these two numbers is 1/4. Applying the same process, we can analyze the computation for other observations 1 and 2. And in the end, we can conclude that the mechanism satisfies log4 pufferfish privacy, since the ratio is no more than 4, and is no more than 4 and not less than 1/4. And we can consider another scenario here. Consider a data set of 2 persons, including Bob, where each can be infected with a disease independently with probability p. We still ask the same query: how many in the data set have this disease? And the truncated 1/2 geometric mechanism is applied. Due to these assumptions, the prior distribution of the true answers is pi equals to this vector. These probabilities here can be computed by the independence assumptions of catching the disease. And the discriminative secret pair here is that Bob is in the dataset with the disease, and Bob is not in the dataset. Then the new initial distributions are pi1 equals to 0, 1 minus p, since 0 couldn't be the answer if Bob gets the disease and he is in the dataset, and pi2 remains as pi. So apply the same process, we compute all the observations probabilities for 0, 1, and 2. And here's the table summarizing these computations. And we can prove that the ratio for each observation is not larger than 2 and not less than 1/2. Thus, the mechanism satisfies log2 pufferfish privacy. Next, we study the pufferfish verification problem. The formal definition is as follows. Given a set of secrets S, a set of discriminative secret pairs S pairs, a set of data evolution scenarios D and epsilon, a positive number, along with mechanism M in a hidden Markov model H, where probability distributions are all discrete, to decide whether M satisfies epsilon pufferfish privacy under these secrets pairs and evolution scenarios is the pufferfish verification problem. However, by showing a reduction from the classic Boolean satisfiability problem, this problem is proved to be NP hard. Nevertheless, we develop an algorithm to verify epsilon pufferfish privacy on any given HMM H with initial distributions pi and tau, which is to check whether there exists an observation sequence omega such that under the distribution pi, to get the observation sequence omega is larger than e to the epsilon times the probability of getting omega under the distribution tau. So that next is how we can compute these probabilities. For a fixed observation sequence omega, probability of these two distributions can be computed efficiently. And to search for all observation sequences in each step, we use a SMT variable W to choose an observation in omega. And we also use SMT ITE expression, if then else, to select current observation and assign corresponding probability. Here's the ITE expression that choose the current observation. If W equals to omega 1, then the observing probability is O as omega 1. Otherwise, the probability would be ITE, the remaining expression. it will search for omega-2 and other observations. Here, we developed the ideas into this algorithm, and the select expression here corresponds to the ITE expressions. We have the theorem that let H be an HMM and pi tau an initial distributions, epsilon a real number, and k an integer. This algorithm returns a SMT query such that the query is unsatisfiable if and only if the probability of this one holds for every observation sequence omega of length k. Next is the evaluations part. We implement the verification algorithm into the tool FAIER, which is Pufferfish Privacy Verifier. We model and verify many classic differential privacy mechanisms in the Pufferfish Privacy framework, such as noisy max and above threshold. The results are summarized in Table 2 in the paper, but we have many interesting findings through the experiments. The first thing is when continuous Laplace noise is replaced with discrete truncated geometric mechanism, the same level of privacy budget epsilon cannot be maintained. The second is even worse. For discrete above threshold, the mechanism cannot satisfy epsilon dp for any value of epsilon. We also investigate into two state-of-the-art statistical testing tools for detecting violations of differential privacy, namely state DP and DP sniper. Compared with the FAIER has advantageous performances concerning efficiency and precision. So for the noisy max mechanism, our verification tool has the most precise result, indicating that 1.373 dp is satisfied, and the algorithm cannot satisfy epsilon dp for any epsilon below this value. Meanwhile, it takes reasonable time to get this result. For the other tools, the precision for epsilon depends a lot on the number of samples set in the testing procedure. If more samples are taken, the precision will be much better, but meanwhile, the time consumed will be much longer. Also, we consider the situation when the size of databases increase. The verification process would be more time consumed to traverse all the states, but this has less influence for testing techniques. Thus, we propose to combine the testing tool and the verification tool to make use of each advantages. Here's the algorithm to compute the lower bound for epsilon, combining FAIER and the state DP. The main idea is to use state DP first to efficiently locate an interval for the lower bound. Then we use FAIER to accurately verify the values in the interval, and meanwhile, we apply a binary search until we finally reach the required precision. So to conclude, we propose the first verification framework for epsilon pufferfish privacy, which specifies privacy mechanisms as hidden Markov models and analyzes privacy requirements encoded in the SMT queries. We studied the pufferfish privacy verification problems on HMMs and proved the NP hardness. We designed an automated verification algorithm and implemented it into a tool, which could catch privacy breaches of the specialized mechanisms. Even for differential privacy, our tool has advantageous performance compared with the state-of-the-art statistical testing tools on finding the privacy budget epsilon. That's my presentation. Thank you.
Thank you so much for your talk. Thank you. And I will start with the question from the in-person audience. if any, if someone can help me. From Philadelphia.
I don't see questions yet.
Okay, there are no.
We just got one on Jeremy.
Yes.
See, there's a question about the remote architecture.
From the audience, so I read the question from AirMeet. So I have two questions. The first one is, did you look at some example of natural mechanism which satisfy pufferfish privacy and doesn't satisfy differential privacy? This is the first one.
Okay, thank you for your question. Actually, we have evaluated many mechanisms that epsilon pufferfish privacy is satisfied, because we only have to specify some scenarios and the secret pairs. And under these considerations, the pufferfish privacy is easily satisfied under these conditions. But the differential privacy has a more standard way to check whether it is satisfied. That is, it has to check whether for the adjacent databases, whether the equations hold. But usually it will has a much larger privacy budget. I don't know whether I answer your question clearly.
Okay, there is a second question from also from Marco Gaboardi. And in your previous work, you used Markov chains and Markov decision processes. Can you clarify why here you use hidden Markov models instead?
Yes, thank you. And here is the reason that we use the hidden Markov models. Since we can only get an output, we can only observe the output in a mechanism, and we cannot observe the state in the mechanism. So this corresponds to the partial observability of the HMMs. And moreover, there are some mechanisms that cannot be modeled by Markov chains. And it needs other treatments, such as using determinism to treat with that with these queries. But in HMMs, it is more convenient to model it, and usually it will cause a model with smaller size than with Markov chains or with MDPs.
Okay. Perfect. If there aren't any questions, so let's thank the speaker again.